So, what if I told you that the tiny engines running our entire modern world, I'm talking about catalysts, have been hiding a secret, a pretty big one for almost 50 years, a secret buried deep inside their structure that could, well, change everything?
Take a look at this. It visualizes a world we really thought we knew inside and out. For decades, the story was simple. All the important chemistry, all the magic, happened right there on the surface of these materials. But this image, it hints at something way more profound. What if the real action isn't on the surface at all, but buried deep within the catalyst's core?
Now, to really get how big of a deal this discovery is, we first have to understand the story that's been told in science textbooks for, like, generations.
Okay, so first things first, what exactly is a catalyst? Well, the easiest way to think about it is as a chemical matchmaker. Seriously, it grabs different molecules, shoves them together so they can react way, way faster than they normally would, and then it just walks away, completely unchanged. They're absolutely critical for everything, from making fuel to scrubbing pollutants out of the air.
For the longest time, this is how science saw catalysts. You have the surface, that was the busy factory floor, the place where all the real work got done. And then you had the interior, what they call the bulk. That was just seen as a passive support scaffold. I mean, yeah, it was structurally important, but everyone believed it was completely inactive in the reaction itself, just sitting there.
And look, this wasn't just some casual idea. For nearly half a century, this was the foundational story of catalysis. The surface did all the work, the inside did nothing. End of story, or so we all thought.
But that long-held story was about to get a major rewrite. A team of researchers decided it was time to look a little closer. And in doing so, they saw something that had been completely unseen for decades.
So you have this team at the Dalian Institute of Chemical Physics, right? Led by Professors Tao Zhang and Yongqing Huang. They decided to challenge that old story. And they used this incredibly powerful microscope to do something that was pretty much unprecedented, to literally watch individual oxygen atoms moving across catalyst particles in real time.
And what they found was just stunning. As one of the researchers, Professor Wei Lu, put it, a channel has been disclosed. What they discovered was that the boundary between the metal and its support material acts like a tiny atomic-scale guard, basically opening a secret door for oxygen to travel where it was never, ever supposed to go.
A secret door, an internal pathway. So what is this thing? What does it actually look like?
Well, the phenomenon has a name. It's called bulk oxygen spillover. It's a total game changer. Instead of oxygen atoms just skating along the surface like everyone thought, they're spilling over and moving through the bulk, the very interior that was supposed to be completely inactive.
And get this, we're not talking about some deep, vast tunnel here. This hidden atomic highway is located just 3 to 5 atoms below the surface. It's a whole secret world operating on a scale that is just unbelievably tiny.
Let's go back to this image again, but now let's look at it with our new understanding. See those red oxygen atoms? They're not just bouncing around on top. No, they are traveling through the blue support material, creating a hidden supply route directly to that silver particle where all the action is.
So why is this so important? Well, as Professor Yongqing Huang explains, this secret pathway enables the bulk, which is otherwise inaccessible, to contribute. That supposedly inactive scaffold, turns out it's a key player in the whole process.
So what happens now? I mean, this discovery does way more than just rewrite textbooks. It opens up a whole new dimension. The future of catalysis isn't flat anymore. It's 3D.
It really is like discovering a whole new network of highways on a map you thought you had completely memorized. This hidden pathway changes everything about how we design and use catalysts.
The shift in thinking here is just massive. The old model was basically two-dimensional. A flat workspace, that's it. But the new model, it's three-dimensional. It reveals this incredible synergy, this teamwork between the surface, the interface, and the bulk, all working together. The catalyst is no longer just a flat table. It's a dynamic, living system.
And this is where it gets really exciting. As Professor Tao Zhang, the team's leader, points out, the goal now is to actively engineer this synergy. It means we can go beyond designing flat surfaces and start creating these complex, three-dimensional architectures for catalysts that can be way more efficient than anything we've ever built before.
This whole thing leaves us with a really powerful question, doesn't it? For 50 years, we've only been using part of the tool. Now that we know about these secret internal pathways, how will we engineer them?
How will we build smarter catalysts for everything from cleaner fuel to more powerful batteries and really, truly design a more efficient world right from the atom up?